everyone. We will be learning a data structure a day for the next few weeks, and today's data structure is called priority queues. What's a priority queue? Well, it's a little bit like a dictionary in the sense that it also stores entries. And you will recall that every entry consists of a key and an associated value. However, a dictionary is used when you want to be able to look up a particular key. A priority queue is used for something completely different, when you want to prioritize entries. And so each key is going to have either a numerical value or some other value that you can order, like alphabetically or numerically or whatever. And so there's a total order defined on the keys. And the operations that a priority queue allows you to do, there's three main ones. And here's two of them. You can identify or remove the entry that has the smallest key. And the catch is that's the only entry that you're normally allowed to identify or remove, at least the only one that you can remove quickly. Technically, it's possible to remove other entries, but it could be really slow. But this limitation that you can only identify the minimum entry or remove the minimum entry is a big part of what makes priority queues fast. The other thing that you're allowed to do is insert anything you want at any time. So it's very flexible about insertions, just not about finding and removing stuff. Now, suppose we use integers as our keys, for instance. Here's an example of what our priority queue might look like. Initially, it might have two entries in it, and suppose they're keyed on the numbers 4 and 7. And those keys have associated information with them. The details of that information doesn't matter too much right now. And so one thing I can do is I can insert, like I said, any key at any time. And so there's an operation, insert. You provide a key and a value, and that modifies the priority queue so that it contains your new information. Like, for instance, if my key is 5, and here's some associated value, then that's what gets put into the table. The way that Goodrich and Tomasia define this insert method, the insert method also returns to you an entry object which has references to its key and its value. I'm not sure why they do that, though, but if you want the entry object, they return it to you. And then you can do remove min relatively quickly. And that does two things. First of all, it updates the priority queue so that the minimum item is gone. And the other thing is, as the return value, it returns to you the value, the complete entry that just got removed from the priority queue. And then finally, there's also a min operation, which basically does the same thing, except it doesn't actually change the priority queue. It just returns the smallest value in the priority queue. And it returns, again, the full entry, the key and the value. So that's what it does. Any questions about this so far? good question you could ask is, why does it do this? And what these are used most commonly for is as event queues. And the idea is that there's a bunch of entries on the queue. The key associated with each entry is the time when an event is going to take place. And the value associated with that key is what the event is, a description of the event that will take place. So again, in that case, the key is the time that the event takes place. And the associated value is a description of the event. So for instance, in a forest fire simulation, you might know that a certain tree is going to catch fire at time 7 because the tree next to it is already on fire. And so you put that event into your priority queue. And maybe you know some other events are going to happen. The fire service is going to arrive at time 9 and start shooting their hoses at the blaze. Now what you do is you take all the events you know they're going to happen and you stick them into the priority queue, and you can insert them in any order. And then to perform the simulation, you just start taking events off the queue one at a time and processing them. And the idea is you want the events to be simulated in the order that they occur. Therefore, you always want, when you're ready to process a new event, you always want to process the event with the minimum time. That's the event that's going to happen next. So maybe you take an event off the queue, and sure enough, your tree catches fire. And so you decide, well, since this tree is on fire now, it's going to set the neighboring tree on fire at time 12, and the tree is actually going to burn up and fall over at time 15. And so later on at time 15, you can, well, first, so you take those new events that are caused by the present event, and you put them on the priority queue so that when the time comes, those events will be processed. And then maybe at time 15, the tree falls down and clobbers some poor firemen or something. And you go on from there. So that's what, oh, question? That's fine. Right, so if you have a bunch of events that happen at the same time, that's fine. You certainly can't outlaw events happening at the same time, but it is true that they will be dequeued one at a time. So one of the, if 10 events are going to happen at time 7, one of them gets dequeued arbitrarily, and there's no guarantee which one. So if it matters to you that you treat them as simultaneous and not a sequence, then your simulation will have to take that into account. It'll have to check, after it removes an event, whether the next event on the queue has the same key or not. Or maybe you can just pretend, it's good enough to pretend that the events happen a millisecond apart, and that's good enough for your accuracy of your simulation. It really depends on the particular application. Other questions? So I'm going to spend the rest of this lecture talking about how to implement this efficiently. And the simplest and generally pretty fast in practice implementation uses a data structure called a binary heap. So again, a priority queue is an abstract data type, and binary heaps are a particular implementation of that data type. A binary heap is, well, its definition encompasses several things. First of all, a binary heap is a complete binary tree. So you all remember from last lecture what a binary tree is, but what's a complete binary tree? A complete binary tree is a tree in which every row of the tree is full, or every level of the tree is full, except possibly the bottom row. The bottom row may or may not be completely full, but if it's not completely full, then you have to fill it in from left to right. Okay, so here's an example of what one of these suckers looks like. So you'll notice that every node in the first two levels has both a left and a right child. Now, the very bottom row is filled in from left to right. So the 9 has 2 children, the 6 has a left child only, and everyone after that has no children. And so that's an example of a complete binary tree. But that's not the complete definition of a binary heap. A binary heap also has to have one other property. The entries in a binary heap satisfy what's called the heap order property. Which I define to be the following. No child has a key less than its parent's key. So if you look at this binary heap I drew over here, you can see that it satisfies the heap order property. For instance, the root node 2 is less than both of its children. This 5 is less than both of its children. This 3 is less than both of its children, and so on. Now, because binary heaps are complete binary trees, they're often stored as arrays, and they're stored in the array in an order that follows a level order traversal of the tree. So let me draw that next to this tree I've got right here. I'll have an array. Now, what I'm going to do is I'm going to not use index 0, just to make the array indexing work out really nicely. But then I'm going to put the root in index 1, and the rest of the tree I write out in level order. So that's, here's the first level, here's the second level, and then finally the third level of the tree. So it fills up an array quite nicely. And again, we're just going to intentionally leave index 0 empty because it makes the indexing work out more nicely in what I'm going to do next, which is to point out how parents and children relate to each other in that array. So the mapping of nodes to indices is also called level numbering. And level numbering makes it really easy to pick out children and parents of particular nodes based on the index of a particular node. Specifically, if you want to know about node I, what are its children and what is its parent? Well, node I's children are 2i and 2i plus 1. And I's parent is I over 2 rounded down. So if I is odd, you round down, which happens to be what Java does when you divide an integer by 2 anyway. So it's really easy to find a node's neighbors when you use this level numbering. You want to know about this 9 here? Well, the 9, its index is 4. According to the formula, that means its children are 8 and 9. And sure enough, that's where the right nodes. And its parent is stored at index 2, and that's the node we find here. So are there any questions about this? Yes? Well, if the 3 only had a left child and didn't have a right child, then this would still work as long as you leave this entry blank. But if you do more than leave this entry blank, if you like shift all these guys over one slot, then this indexing isn't going to work at all. But the reason we want a complete binary tree is not just so that we have this numbering, but it's for another reason too, which is so that when we insert and delete items later on, the heap will stay compact, which is another nice thing that we want. Other questions? So one of the reasons, well, why I'm talking about an array, well, you could use a pointer and node-based data structure to store a binary heap. There's no reason why you couldn't. So, any standard binary tree or even general tree data structure could store this. But when you use this array representation, the code just runs a lot faster because you don't have to worry about setting and resetting references from one node to another. You don't have the expense of creating objects in the first place, and, well, except for the one array. And so the reason why this representation is popular is when you write a heap implementation with this kind of array implementation, it just burns rubber. It's just really fast. Also, if you use a tree representation, then you always have to keep track of where the last node of the level ordering is, which is a nuisance as well. And with the array, well, you just always know, because you know how many items are in the heap, so you just know where the last item is located. If there's 10 items in the heap, then the last item is located in index 10. So each tree node has, well, in this diagram, I have just drawn the keys. I've just drawn the numbers. I have not drawn the values. So I just want to remind you again that there could be a value associated with each of those numbers. And there's two ways you could store that. Either each tree or array reference say each tree node has two references. one for the key and one for the value. Or your other alternative is you could actually have an entry object and the entry object has references to a key and a value. And so Goodrich and Tomassia use the entry object. And if you want to see how that's defined, go look on page 322 of Goodrich and Tomassia. Now, for the array representation, this is convenient because the array just has a bunch of references to entry objects. But if you wanted to do it this way, then you would use two arrays. One array would have the key objects, and one array would have the value objects. So now let's look at how we will implement the three operations on a binary heap. The first operation is the min operation, which just returns an entry. And that entry is the entry with the minimum key. Well, that one's really easy to implement because the heap order property guarantees that the item, the entry with the minimum key, is always at the root of the tree. So just return the entry at the root. And that's it. Very easy. So let's look at a tougher operation. All right, the insert operation takes a key and a value. You have to have some way to compare the keys, but the key could be any object and the value could be any object, as long as the keys are comparable. This one's a little trickier because we need to take an arbitrary key and somehow get it to fit into this heap so that the heap order property is still satisfied. And so here's how we're going to do that. First of all, a little notation. Let x be the new entry, which is an ordered pair consisting of the key and the value. We're going to start by placing x at the bottom level of the tree in the first open spot. And if the bottom level is all full up, then you start a new level and you put the new key at the far left. So one of the nice things about this is that that means you're always putting the new key at the first free entry of the array. So if I've got 10 items in my array, the new one will go at index 11, at least starting out. Now, the problem with that is that, of course, the new key might violate the heap order property. So maybe I'm inserting a 2. So I start with this heap, and I decide I'm going to insert a 2. Well, the heap order property says no child has a key less than its parent. And here's a child that has a key less than its parent. So we got to fix that up. And the way we fix it up is that the entry bubbles up the heap. It goes up through the tree until the heap order property is satisfied. So what do I mean by bubbles up the tree? Let me be more specific. Here's the algorithm. We're going to repeat the following over and over again until we're done. We're going to compare x's key with its parent's key. And if x's key is less, then we exchange x with its parent. And then we just repeat that over and over again until x can't move up anymore. So, for instance, in this example, x is the new node with key 2 that we've just inserted, and its parent has a key of 6. So we're going to swap those two entries. Okay, so now x has moved one step, one level up the tree. And now we repeat that loop. Once again, we compare x with its parent. And now its parent is 5. So we got to take another step. Oops. And now we do it again. Our key x has now moved up to level 1. We compare it with its parent, and it is not less than its parent, so we can stop and we're done. One thing you'll notice, by the way, is that it's perfectly fine, again, for a binary heap to have 2 copies or lots of copies of the same key. Questions? Yeah, over in the far. Yes, sir. Uh-huh. This one here? So the question is there ever a situation where the key might have to go back down again because it turns out to be greater than its sibling? So let's take a look at this. So this 2 here is the invader, the new key that we're inserting. But before we inserted it, everything else obeyed the heap order property. And so what that means in particular is that this key here is greater than or equal to its parent. So we know this has to be greater than or equal to that because it was a heap before we started. And if we make the decision that we're going to swap these two, then the only reason we would do that is because we know that this one is less than its parent. So if you put this inequality and this inequality together, we've got clearly that this has to be less than this. and therefore it'll never go back down the tree. It's a good question. Other questions? Yes, in the back. What if the 5 was a what? Well, if the 5 was a 9, then we even violated the heap order property right here, so we didn't have a heap in the first place. Now, if we start off with something that's not a heap and we apply this algorithm, it's not going to fix the broken heap. So this algorithm only works if we started with a perfectly good heap. Other questions? You can do a mathematical proof that if you start with a good heap, this always ends with a good heap, but I'm not going to go through the drudgery of that. All right. Do this. The other major important operation is how do you remove a key? So we have a remove min operation, which removes the minimum key and also returns it at the same time. This is just a little bit more complicated than insert. It also involves bubbling through the heap, but in a different way. We're going to start by removing the entry at the root node. Because you'll recall that the minimum item, or the minimum key, is always at the root because of the heap order property. So we can take the entry at the root and remove it and save it for the return value. Before we can return, though, we have to fix the heap because now it's rootless. So we've got a big hole, a big gaping hole at the root. We want to fix that hole. So what we do is we fill the hole with the last entry in the tree. Or in other words, the last entry in the level ordering of the tree. So we're going to take this key from the bottom of the tree, and we've got a hole here. We're going to take that and move it up to fill the hole. Problem with that is that, of course, the thing that we've moved up to fill the hole is almost certainly not going to be the minimum key in the tree. So we, once again, need to fix that. So this last entry in the tree, let's call that x, just so that I have a shorthand for it. So x is this guy here. This is moved up to the root of the tree. Now we're going to bubble it down through the heap. And so here's the algorithm for that. We're going to repeat the following as many times as necessary. If x, the node we've just moved to the root, is greater than one of its children or both of its children, then swap x with its minimum child. Now, notice that I did not say swap x with any child that x is bigger than. I said swap x with its minimum child. So if x is bigger than one of its children, you have to check both children and figure out which child is the minimum one, because that's the only one that is eligible to move up. And so that's the algorithm. Let's see how this works. So again, here's the heap that I started with, my example heap. If you want to do remove min on this, then the first thing that happens is that the 2 disappears from the top. The 8 moves up to take its place. And so we have, temporarily, a broken heap. Broken because the root node is bigger than both of its children. But one of the nice things about a heap, and actually something that I should have said earlier, is every subtree of a binary heap is a binary heap. So if you go back and you look at this original binary heap, then not only is the whole thing a binary heap, but the portion of it rooted at 5, that's a binary heap too, because it satisfies the heap order property, and because it's still a complete tree. And the subtree rooted at 3, that's a complete binary heap as well. So when I take this 8 and I move it to the top, okay, I've broken my binary heap, but I still have the nice advantage that this is a binary heap. And this is a binary heap. The reason why this is good news is because in a binary heap, the minimum key is always at the top. Now, I want to fix the entire binary heap. So I want the minimum key in the entire heap to be here. Where do I find that minimum key? Well, there's only 2 places that it could be. Either the minimum key is here at the top of this binary heap, or it's here at the top of this binary heap. Unless it's this one. So there's 3 places that the minimum key could be. So I just need to figure out which of these 3 is the minimum key and move it to the root, and I've got the right root. And so that's what this algorithm does. It compares x with both of its children, and if x is greater than either of its children, or both, as in this case, we swap x with its minimum child. And the minimum child here is the 3. So the 3 moves to the top. The left subtree, since it didn't change, is still a binary heap. So this one's good. That's still a binary heap. The right subtree, well, now that's broken, because I've just messed up the root of that binary tree. So this is not a binary tree anymore. But this is a binary tree, and this is a binary tree. So I just repeat the logic over again. I've messed up here, but I have 2 binary trees here. The smallest out of all of these keys has to be one of these 3. So I pick the smallest one and I move it up. And that's my next step. And then this part's the same. And that is how you delete a key from a binary heap. Question? Yes? What if instead of 5 you had 2 3s here? Then it doesn't matter which one you swap with. Either one will do. Pardon? The left or the right. So yeah, you could swap this. If this is a 3 and this is a 3, you could swap these two and it'll work just fine. You could swap these two and it'll work just fine. You get to choose. Write your code however you like. In the back. Well, what happens to your array is that you're actually executing all of this in an array, usually. When you actually sit down to write the code, you are swapping, every time you do one of these swaps, like swapping these two, you are swapping 2 items in the array. And there's nothing really special about it. It's just that you write the code that uses the level numbering system here, so you know what the children of each node are, you know what the parent of each node is, and you use the index just as if you were using a tree. You never have to create a new array with this. That's one of the really nice things about it, is that when you do this, for instance, your array looks like this. You've got your level numbering. Yeah, I guess I should animate this. That's what I should do. Okay, so here's the beauty of it. There's my array. What I'm going to do is I'm going to start. I know I want to do remove min. I know that the minimum item is always at the root. So I take this item and I store it to return at the end. And I take the very last item and I move it to the root. So now I know that the item that I need to fix up is in index 1. And the children of 1 are 2 and 3. So I check which of these are either of these smaller than this? Yes. Which one's the smallest? Index 3. And I swap them. Okay. Now my key is at index 3, so I know its children are 6 and 7. 4, 5, 6, and 7. And so I compare them. Is 8 less than both of those? No, it's greater than 4. So I have to swap these two. And now the children of 8 are bigger than the end of the array, so there's nothing more to do. And I'm done. If I were to add one? If I were to add one, then either you have to have extra room at the end of the array, or if you run out of room in the array, then you have to resize, just like a hash table. You're right. Question? You would have to ask Goodrich and Thomas-Sia. It's their idea. I have no idea why they do it. But when you insert a key into value, they give you back the entry object that points to that key and that value, just in case you happen to want it for some reason. Yes? The only way to do max with this particular data structure is to search through the entire heap, and that takes linear time. But you can have what's called a max heap, where you reverse the heap order property so that the maximum key is always at the root, and then you can find maxes as fast as you want, but now you can't find mins fast anymore. So you have to pick one. Either you have a min heap where you can do min operation fast, or you pick a max heap where you can do the max operation fast. It doesn't do both. Running times. So there's more than one way you could implement a priority queue. There's the binary heaps that I've just taught you, but there's also some really obvious ways you could do it with, say, a sorted list or a sorted array. Or you could do it with an unsorted list or an unsorted array. And so I want to not only tell you about the running times for binary heaps for these operations, but also I want to compare them against the obvious alternatives for how you could do this. Well, so doing a min operation in a binary heap, you just look at the root, so that takes constant time. In a sorted list, since the list is sorted, you can always find the minimum item in constant time. And if you have an unsorted list, you have to search through the whole list because it's not sorted. So that's going to take linear time, which is slow, especially if you're doing a lot of min operations. The insert operation, well, we could talk about the worst case time and the best case time. The worst case time is the more important one for sure, but it's also kind of interesting to see what happens when you get lucky. In a binary heap, insert takes log n time in the worst case. And I will talk more about that in a minute, why that is so. But in the best case, you might get lucky. Your key might be the largest item in the whole heap or something, and you won't have to do any bubbling because it'll already be in heap order property as soon as you insert it at the bottom. Now, if you try doing this with a sorted list, then inserting an item into a sorted list, you have to find the right place in the list to put that item. And so that's going to take linear time in the worst case, of course. You might get lucky in the best case. So it could take theta 1 time if you're lucky, but you're usually not that lucky. With an unsorted array, well, you can just insert something by sticking it at the end of the list, or at the beginning of the list, whichever you prefer. So that can be done fast. And finally, there's the running time of remove min. So removing the minimum item in the worst case for binary heap again takes log n time. And in the best case, well, if all of the items in the heap have exactly the same key, then you won't need to bubble the key down, and it'll take constant time. In a sorted list, removing the minimum key is easy because it's at the very beginning or the very end of the list, depending on how you sort it. And in an unsorted list, removing the minimum key means finding it, which we already know means you have to search through the entire list. Now, the next thing I'm going to do is talk about where these log n times come from, but are there any other questions? Yes? For unsorted list, best case, sorry, which one? Remove min or? Well, so there's no way to know that you have the min unless you've checked every key. Yes, sir. Okay, so if you have a sorted array and you want to do an insert, it's true that you can find the right place to insert the item in log n time because you can do binary search. That's true. But once you've found the right place to insert the item, you have to actually insert it, and that on average means you have to push half the items in the list over one space to make room for the new item. And that's what's going to take linear time. And there's no easy way around that. Other questions? So about this log n time stuff, insert, as we know, puts an entry at the bottom of the tree and bubbles it up. At each level of the tree, it takes constant time to compare x with its parent. But how many times does it have to compare x with a parent? Well, every time it bubbles up a step, it has a new parent that it has to compare with. Now, since the binary tree, since it's a complete binary tree, here's where this is very important. Because the binary tree is complete, meaning we never start a new level until we've filled in all of the previous levels, it has, at most, 1 plus the base 2 logarithm of n levels, where n is the number of entries in the heap. And so that is why when you're bubbling up or bubbling down, you've got theta log n worst case time. And the same argument applies to remove min. Since there's only 1 plus log n levels in the tree, you can only do log n bubble steps down the tree before you're done. Any questions about that? So there's one more operation we want to learn about. It's called bottom-up heap construction. What this is about is, suppose someone just gives you a big bunch of events in random order and you want to make a heap out of them. Well, the simple way to do this is insert them one by one. And if you do that, each insertion could take log n time, so the whole thing together could take n log n time. We can do better than that, it turns out. There's a way to do this in linear time. And here's how you do it. First of all, you just make a complete tree. Out of the entries in any order. So if you're using an array-based heap, this means you just take your entries and you throw them into the array in any order. And now you have a very broken heap, so here's how we're going to fix it. You walk backward through the level ordering, or through the array, from the last internal node An internal node is a node that's not a leaf. To the root. Or in other words, you walk through all the elements in the array in reverse order. And for each internal node that you visit, you bubble its entry down. Just like we do in remove min. So here's an example. thrown a bunch of numbers into an array, or into a complete tree. This is the last internal node in the level numbering, since this one is a leaf. And so I'm going to take that 7 and bubble it down. And now I get this. Okay. Then I go back one step in the level numbering to this one, and I bubble that one down. And I go back another step in the level numbering. And finally, I'm at the root, and I bubble that one down. And when I say bubble down, I don't just mean one step. I mean as far as it needs to go. And so that needs to go 2 steps down. So we wind up like that. Now, I'm not going to prove it here, but the running time for this is in linear time. And if you want to see a visual proof of that, there's a really lovely one on page 355 of Goodrich and Thomasia. It's really simple and cool, so you should go look at it. Page 355. Any questions?